Hello, everyone. I hope you're all safe and sound. Welcome to the 15th lecture on analog and digital electronic circuits, in which I will introduce the low frequency response of amplifiers. And in particular, we will study the low frequency response of a fully bypassed common emitter amplifier. So far, we have analyzed the amplifiers in the mid-band frequency range, in which the capacitive reactance of coupling capacitors is small enough and the capacitive reactance of internal capacitors is large enough to be ignored. However, as we decrease the frequency, the capacitive reactance of coupling capacitors increases, and below a particular frequency, the reactance becomes large enough that we cannot ignore it anymore. So on the lower frequency side, in the low band, as shown in this diagram here, we have to analyze the amplifiers by taking into account the effect of coupling capacitors. However, on the other hand, if we increase the frequency, then the capacitive reactance of internal capacitors, it decreases. So beyond a particular high frequency, the capacitive reactance of the internal capacitors becomes small enough that it cannot be ignored anymore. So in the high band, which is shown in this diagram here, the amplifier is analyzed by taking into account the effects of the internal capacitors. Both of these effects, that is the effect of coupling capacitors on the low frequency side and the effect of internal capacitors on the high frequency side, these two effects, they tend to decrease the gain of the amplifier below its mid-band value. So on the lower side, we only take into account the effects of coupling capacitors, because as we decrease the frequency, the capacitive reactance decreases, and the approximation that the the capacitive reactance increases with the decrease in frequency. So the approximation that the internal capacitors are open circuit becomes even better. Similarly, at the high frequency, when the capacitive reactance decreases, then the approximation that the capacitive reactance of coupling capacitors is almost zero, it becomes even better at high frequency. So in the mid-band, we do not take into account the effects of capacitors. On the lower side, we take into account the effects of coupling capacitors on the response of the circuit, and on the higher side, we take into account the effects of internal capacitors on the performance of the circuit. So these capacitive effects, like I said, they tend to decrease the gain below the mid-band value. So the frequencies at which the gain decreases by 3 dB below its mid-band value, these frequencies are called the cutoff frequencies. So on the lower side, it is called the lower cutoff frequency, denoted by F subscript L, and on the higher side, it is called the higher cutoff frequency, denoted by F subscript H, capital H. And the difference between these two values, the range of frequencies between FH and FL, is called the bandwidth of the amplifier, which is denoted by dW. So we know that the capacitive reactance is inversely proportional to the capacitance, and it is given by this expression, where C is the capacitance of the capacitor, F is the frequency, and J is the mathematical iota, which introduces a phase of 90 degrees. So it makes the capacitive reactance purely imaginary. So replacing 2 pi f with omega, which is the angular frequency, we can we define a new complex frequency variable denoted by S, which is equal to J times omega, or in other words, it is equal to J times 2 pi times the frequency of the signal in hertz. So since the capacitive reactance is now a function of the complex variable S, the response of the circuit, which will inevitably depend on the capacitive reactance of the capacitors in the circuit at the low frequencies, will now inevitably be a function of S. So this response, the ratio, for example here, the ratio of the output voltage to the input voltage, which is written as A, is now a function of the complex variable S, and is called the transfer function of the amplifier. Since it is a complex quantity, it can be written in polar form with the magnitude and phase. So this magnitude, the plot of this magnitude against the frequency is called the magnitude response of the amplifier, and the plot of this phase against frequency is called the phase response of the amplifier. So to further elaborate on the low frequency response of amplifiers, I will analyze the fully bypassed common emitter amplifier at low frequencies, the circuit of which is shown in this diagram here. So you can see that this bypass capacitor is connected directly at the emitter terminal. So at AC in the midband, this completely bypasses the resistance RE, and the AC equivalent circuit of this fully bypassed common emitter amplifier in the midband has emitter at AC ground. But now we will be analyzing this circuit at the low frequencies, in which we cannot ignore these capacitors, coupling capacitors, as well as the bypass capacitors anymore. However, analysis of this circuit, considering all the capacitors, is a mathematically challenging task, which is why a common and an approximate approach is to analyze the amplifier at low frequencies by considering one capacitor at a time. So I will consider the effect of C in, CE, and C out separately, one at a time. So starting with the effect of C in on the response of the amplifier, here I show the AC equivalent circuit of the fully bypassed common emitter amplifier with C in connected. So as you can see that CE and C out have been assumed as short circuited. So because of that, the emitter resistance RE has been bypassed, and the emitter terminal is directly at AC ground. So because of this ground here, we see that V pi now becomes equal to the input voltage Vi, because V pi is the voltage between base and emitter. Emitter is grounded, so it is the voltage. It becomes equal to the input voltage of the amplifier. And it is a function of the complex frequency variable S, because now it is given by the voltage division of V sig between R sig, C in, and Vi. And the division is now controlled by the capacitive reactance of the input coupling capacitor, which is why this is now a function of S. So Vi is given by R1 in parallel with R2 in parallel with R5. So Vi is Ri, which is the resistance between this base terminal and ground looking towards the right of the circuit, divided by Ri plus R sig plus the capacitive reactance of C in times V sig. So where the capacitive reactance is a function of S, which makes Vi a function of S. And like I said, the input resistance Ri is given by the parallel combination of R1 in parallel with R2 and R5. So from the analysis of fully bypassed common emitter amplifier, we know that the output load voltage is given in terms of the input voltage of the amplifier through this expression. So and then we can replace Vi with this expression, and we'll get VL in terms of V sig through this expression. So VL as a function of S divided by V sig is given by this expression, in which we can explicitly write the denominator as an inverse like this, where I replace XC in with 1 over S E in, and taking Ri plus R sig out common from this term into the denominator, I'll be, and then keeping the other terms as it is, we'll be left with 1 plus 1 over S times Cn times Ri plus R sig. So taking the LCM, taking the inverse, and then dividing the numerator and denominator with the Cn times Ri plus R sig will enable us to write this term like this, in which RIB is the resistance seen looking into the base. So the resistance seen looking between this terminal and this terminal into the base is given by R pi because of the AC ground altimeter. So RIB is just R pi. So we can see that this term, this pre-factor, is independent of the frequency, and in terms of the frequency, it is a constant, whereas this represents the response of a single time constant network. A single time constant network or an STC network, as the name suggests, is a circuit which has single time constant, such as a low pass or a high pass filter. So we can, and in particular, we see that this is the response of a high pass filter. So we can write it in this form, where AM is the frequency independent term, which upon close inspection can be seen to be equal to the gain of the amplifier in the mid-band frequency range. That is when the effects of all the capacitors are ignored, then the gain of the amplifier is given by this term. So we replace it with AM, and we call AM as the mid-band frequency gain of the amplifier, and it is obviously independent of the frequency. Whereas the other term, this term in the denominator, which is the inverse of this R C time constant, it is called as it is denoted by omega subscript Tn, and it is called as the break frequency or the corner frequency, or more commonly the pole frequency. So I denoted with omega p subscript n, which represents the angular pole frequency due to the capacitor Cn. So this actual exact expression of the mid-band gain can be well approximated under the assumption that R0 is very large. So if we assume R0 to be infinity, then dividing this numerator and denominator by R0, we are left with the beta RC in parallel with RL, and in the denominator we are left with 1 plus this term over R0. Since R0 has been assumed infinity, so this term becomes 0, so the denominator becomes 1. So we'll be left with beta times RC in parallel with RL, and beta over R pi is equal to GM. So we'll be left with this approximate expression for the mid-band gain of the amplifier under the assumption that R0 is very, very large. So this, like I said, this is a response of this is the response of the common emitter amplifier, fully bypassed common emitter amplifier, by taking into account the input coupling capacitor Cin, and it represents the response of a high pass filter, which can be plotted against frequency, as I have done here in this diagram. So this black curve here is the actual response, is the plot of this equation given in 8. So you can see that it represents high pass filter. It passes all the frequencies which are greater than FP here. So FP here corresponds to the cutoff frequency. It is the pole frequency which is equal to the cutoff frequency. That is, it is the frequency at which this mid-band gain AM drops by 3 dB below AM. So FP here, which is the pole frequency given by 1 over 2 pi times this factor, is actually equal to the cutoff frequency of the circuit. And then the curve shown in blue here is the approximate, or more commonly called the asymptotic response of the circuit. So asymptotic response is obtained by decreasing the gain of the amplifier with a slope of 20 dB per decade, which is equivalent to 6 dB per octave, whenever we encounter a pole in the system. So for frequencies greater than FP, there is no pole, so the gain is kept constant. As soon as we hit a pole, we decrease the gain of the amplifier with a slope of 6 dB per octave, or 20 dB per decade. So this gives us an approximate piecewise response of the amplifier, which is called the asymptotic response of the amplifier. So this asymptotic response helps in a rough, quick analysis of low frequency analysis of the circuit. So you cannot draw this black curve by hand because you need a lot of points to accurately draw this or plot this expression versus frequency. So usually this is done by a simulator. So this is a simulator generated black curve, but this blue curve, which is the asymptotic response, can be easily drawn by hand. So whenever you encounter a pole frequency, just decrease the gain by a slope of 20 dB per decade. So this is a very effective tool, this asymptotic plot. It enables us to, like I said, to analyze the circuit quickly at the low frequency. And from the inspection of this expression here, we see that I've written this resistance Ri plus R sig as RCN. So RCN is actually, so RCN times Cn is actually the time constant associated with Cn, and RCN is the resistance seen by Cn. That is, if I open circuit the terminals of the capacitor Cn and find the resistance between these open circuited terminals at V sig is equal to 0. So I short circuit V sig, I open circuit Cn, and I measure the resistance between this terminal and this terminal. So the resistance between this terminal and ground, in other words, the resistance looking in towards the left between this node and ground, since V sig is short circuited, it's simply R sig. And the resistance between this node and ground looking towards the right is simply Ri. So the total resistance, because this ground and this ground, they're connected, so the total resistance is R sig plus Ri. So R sig plus Ri is the resistance seen by the input coupling capacitor Cn. That is why I've written it as RCN. And this is a trend that we will see later on as well for the other capacitors. That is the approximate analysis of the amplifier by taking into account the other capacitors will also yield a pole frequency, which pole angular frequency, which will be given by the inverse of the respective time constants, in which the time constant will be given by the value of the capacitance of the capacitor and the resistance seen by the capacitor at V sig equal to 0. So this is a very important result. This helps us in avoiding this analysis, and by simply writing the response like this, where we can quickly find out the pole frequency as the inverse of the time constant of the associated time constant associated with the capacitor under consideration. And that time constant is found by multiplying the capacitance of the capacitor with the resistance seen by the capacitor at V sig equal to 0. So now we will proceed towards finding the response of the circuit by taking into account the coupling capacitor, the bypass capacitor CE, by assuming the coupling capacitors as short circuits. So for mathematical simplicity, I will ignore R0, because if we include R0, then the resulting expressions will become mathematically laborious. So I'm going to ignore small R0. And by looking at the circuit, we can find the total emitter resistance, that is the resistance between emitter and ground. That total AC resistance is now given by the parallel combination of RE and the capacitive reactance of CE. So it is represented as VE. It is the parallel combination of RE and the capacitive reactance of CE. So again, from the analysis of common emitter amplifier, we can write the load voltage like this, and in which RID is the resistance seen looking into the base, which is given by R pi plus this impedance shifted towards the base. So when we reflect this resistance to impedance towards the base, it is multiplied by beta plus 1. So R pi plus beta plus 1 times VE is the resistance seen looking into the base. So and then VI is simply given by the loading factor Ri over Ri plus R sig times V sig. So we take V sig to the other side, and the ratio of VL to V sig is given by this expression. So Ri is the input resistance of the amplifier and is given by R1 in parallel with R2 in parallel with RIB, the resistance seen looking into the base. So this is Ri, and then we can open up the numerator, R1 in parallel with R2 times RIB over R1 in parallel with R2 plus RIB. This RIB will get cancelled with this RIB, and this fraction will become beta times RC in parallel with RL, and then we can open up this, expand this denominator as well, in which we open up this parallel combination. So by taking the LCM, we get this term, and then we can cancel this numerator with the denominator, and we'll be left with beta times RC in parallel with RL times R1 in parallel with R2 times this numerator denominator, which is explicitly written as this as the inverse of this term. So again, I can simplify this term by taking R sig plus R1 in parallel with R2 out common. So I'll be left with RB here. And when I take this term out common, I'll have in the denominator R sig plus R1 in parallel with R2. So this numerator divided by that denominator will give me the parallel combination of R sig and R1 in parallel with R2. So this is the term I took out common from this term here. So because of this inverse, that term which I took out common will appear in the denominator of this term. So I can expand RIB by replacing ZE with RE in parallel with 1 over SCE, and R pi is beta plus 1 times small RE, so I can take beta plus 1 out common, and this is what I'll get. And I can again take R sig in parallel with R1 in parallel with R2 plus beta plus 1 times small re out. And this will come in the denominator. This will appear in the denominator. And whatever is left inside, I can simplify by taking the LCM and solve, and then take the inverse. And eventually, I'll get an expression of this form, in which omega PE will be the inverse of this time constant. So it is the inverse of the product of the capacitance CE and RCE, where RCE, which is equal to this term, is again the resistance seen by the bypass capacitor CE. So if we look at the circuit at V sig equal to 0, so if we short circuit V sig, and if I open circuit CE and I find the resistance between this node and ground, then this resistance is equal to RE in parallel with the resistance reflected from the base side into the emitter side. So the resistance reflected from the base side is R sig in parallel with R1 in parallel with R2. So when I short circuit this V sig, R sig is in parallel with this resistance. So this resistance in parallel with this resistance plus R pi. So this total resistance, when shifted towards the emitter, gets divided by beta plus 1. So R sig in parallel with R1 in parallel with R2 plus R pi divided by beta plus 1. So R pi divided by beta plus 1 is small re, and the other term remains as it is. So this resistance, which is shifted from the base towards the emitter side, is in parallel with Re. So this reflected resistance is in parallel with Re, and that parallel combination gives us the resistance seen looking into the open circuit terminals of the capacitor CE. So like I mentioned before, again, the angular pole frequency is obtained by the inverse of the time constant associated with the capacitor CE. That is, it is the inverse of the product of the capacitance CE times the resistance seen by the capacitor with capacitance CE. That resistance is found by short circuiting G6 to 0. So furthermore, we see that from this expression that there is a 0 here. So when S is equal to minus 1 over CERE, then this factor becomes 0 and the overall response becomes 0. So we say that at S is equal to minus 1 over CERE, the response becomes 0. So at S is equal to this, so this S is equal to minus 1 over CERE represents a 0 of the response. However, typically the value of the bypass capacitors is of the order of hundreds of microfarads, and the emitter resistance is of the order of kilo ohms. This results in a time constant which is of the order of 0.1 or so, and hence the inverse of the time constant, which is the magnitude of the zero, is of the order of 10 units or so. This is a relatively small number and hence can be neglected. So the approximate response of the amplifier due to the bypass capacitor at low frequencies is given by this expression, in which this first term, the product of these two terms, they are independent of the frequency, and this last term represents the response of a high pass filter. So the pole frequency introduced by the bypass capacitor CE gives another descent in the magnitude response of the amplifier with a slope of 20 dB per decade, similar to the one I showed earlier. Now, considering the effect of C out on the overall on the response of the common emitter amplifier, we assume that CN and CE are short-circuited, which gives us the input voltage again equal to V pi, and V pi is given in terms of V sig through this voltage division rule, where Ri is the input resistance of the amplifier, which is given by the parallel combination of this resistance and R pi. So now the load voltage is found by finding out, first of all, the voltage between this node and ground, because the voltage at the collector with respect to ground is divided between C out and RL. So the voltage at the collector with respect to ground is minus IC times the total AC impedance between collector and ground. And the total AC impedance between collector and ground is RC in parallel with XC out plus RL. So RC in parallel with XC out plus RL times minus IC gives us the total voltage at the collector with respect to ground. And this voltage between collector and ground is divided between C out and RL. So VL is given by the voltage division of this voltage between RL and XC out, and is given by this expression. So we can open this parallel combination, and XC out plus RL in the numerator will get cancelled out with the denominator, and we'll be left with RC plus XC out plus RL in the denominator. So again, for simplicity, we have ignored R naught. So ignoring R naught, IC becomes equal to GM V pi. So replacing IC with GM V pi and replacing V pi using this expression, we get VL in terms of V sig, and VL over V sig is given by this expression. So in this expression, I wrote this denominator explicitly like this in the form of inverse, and then I took RC plus RL out common, so it appears in the denominator, and I'm left with 1 here plus XC out over RC in parallel with RL. So this becomes equal to the parallel combination of RC and RL, and then solving the term within the parentheses by taking the LCM, because XC out is 1 over SC out, so I can take the LCM here, and I can take the inverse later on, and then I can divide the numerator and denominator with C out times RC plus RL. So I'll be left with this factor here. So again, the product of the first two terms here can be seen to be equal to the mid-band gain of the amplifier. And we can replace this time constant, the inverse of this time constant, with another angular frequency. This time it is the time constant because of P out, so we call it omega P out. So AM is the mid-band gain of the fully bypassed common emitter amplifier, and omega P out is the pole frequency due to the output coupling capacitor C out, and is given by the inverse of this time constant. So I write this resistance here, RC plus RL, as RC out, because again, this resistance is actually the resistance between the open circuited terminals of C out. So RC plus RL is the resistance seen by C out at Vsig equal to 0. So so it basically, because I've ignored R naught, so it doesn't matter if I short circuit Vsig or Vi. But to maintain consistency with the other results, I assume that I have short circuited Vsig. So by open circuiting C out, I can find the resistance between these open circuited terminals. So the resistance between this terminal and ground looking towards the left is RC, and because we've ignored R naught, and that resistance between this terminal and ground looking towards the left is the output resistance of the amplifier, which is RC, and the resistance between this terminal and ground looking towards the right is RL. So since the ground is connected for both of these branches, so the total resistance between this terminal, between this and this terminal, between the open circuited terminals of C out, that total resistance is RC plus RL. So again, RC plus RL is the resistance seen by C out, and so I write it as RC out, and the time constant associated with the output coupling capacitor is given by RC out times C out, and the inverse of that time constant is given by the is equal to the pole frequency introduced by the output coupling capacitor C out. So now the overall frequency response of the amplifier is approximated by the product of the three high pass filter responses due to the coupling and bypass capacitors and the mid-band gain AN. So this approximate response is shown in this diagram here by the black curve. So this black curve is actually the plot of this expression here. Also shown is the asymptotic response in the blue curve. So the asymptotic response is obtained by introducing a slope of 20 dB per decade whenever we encounter a pole. So for frequencies greater than FPE, so here FPE is the largest among the pole frequencies. So for frequencies much greater than FPE, the amplifier is in the mid-band frequency range, and there is no effect of the capacitors on the gain of the amplifier. So the gain of the amplifier is just constant. So as we reduce the frequency, we encounter a pole at FPE. So at that point, we reduce the mid-band gain with a slope of 20 dB per decade. So the gain starts decreasing with a slope of 20 dB per decade until we reach FP out. So FP out is another pole frequency which will introduce another 20 dB per decade, and the gain will now below FP out. The gain will start decreasing at a rate of 40 dB per decade until it reaches FP in. So FP in is the third pole frequency which will introduce another 20 dB per decade. So below FP in, the gain will reduce at a slope of 60 dB per decade. So whenever we encounter a pole, we decrease the gain by introducing an additional slope of 20 dB per decade. So as you can see that this asymptotic plot shown in blue follows very closely this approximate black curve, which is the plot of this overall frequency response of the amplifier. So the lower cutoff or the 3 dB frequency is determined by the highest pole frequency. So as shown in this diagram, the highest pole frequency is FPE. And here in this, by this red dotted lines, I have shown the point at which the gain drops by 3 dB below its mid-band value. So that is equivalent to dropping the gain to 70.8% of its mid-band value. So the frequency at which that happens, by definition, is called the lower cutoff frequency or the 3 dB frequency. And as you can see, that this lower cutoff frequency is almost equal to, in fact, we cannot differentiate between the lower cutoff frequency and the pole frequency due to CE. So since FPE dominates the other two, so the lower cutoff frequency is very, very well approximated by the pole frequency introduced by the coupling capacitor CE. So like I said, FPE is usually the dominant pole frequency because the resistance, the time constant associated with CE is very small because of the small value of the associated resistance. That is, the resistance seen by the capacitor CE is really, really small. Even if we use large value of capacitance for CE, the time constant is still small, and the corresponding pole frequency still dominates the other pole frequencies. So if the pole frequencies are not widely separated, that is, if the pole frequencies are close together, then a reasonably good estimate for the lower cutoff frequency is obtained by summing up all the pole frequencies like this. So given a design constraint on the lower cutoff frequency of an amplifier, it is a good practice to ensure that FPE, which is the pole frequency due to the bypass capacitor, this pole frequency dominates the other two pole frequencies. Because the associated resistance, that is the resistance seen by the bypass capacitor CE, is usually very small. So by ensuring that FPE is a large fraction or a large percentage of the lower cutoff frequency FL, we can minimize the total value of the capacitance used in the circuit, where the total capacitance is the sum of Cin, Ce, and Cout, which is actually desirable because smaller the value of a capacitor, smaller is its size. So smaller value capacitances or smaller value capacitors are desired to achieve the design criteria on the cutoff frequency FL. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.